Welcome to this lecture series in linear algebra. In this lecture, we'll discuss a very important concept of the adjoint of a linear map between two inner product spaces. And let us recall at least two main ingredients that we need to discuss this concept. So first, we need to know what is the transpose of a linear map. So whenever we are given two vector spaces V and W and a linear map between them, we can define the transpose of T as a map from the dual of W to the dual of V, which just takes a functional psi on W to psi composed with T. That's the transpose. And orthogonal decomposition. So if V is an inner product space and U is a subspace of V, then V is the direct sum of U and U perp. U perp is the orthogonal complement of U. So we have seen these things in previous lectures, and now let us continue. Here are some problems for practice. And now let us get started. So first we will prove a very simple lemma. V be an inner product space, then for any functional phi on V, there is a unique vector little v such that phi is this particular functional. So what is this functional? This functional is, this by definition is a map from the vector space to the base field. Again, base field is either real or complex because we are working with inner product spaces. So this just takes x to the inner product with the vector v. And this is a linear map, one can easily verify. Okay, so every linear functional is of this particular kind is what we are trying to prove. Okay, so let's prove the existence and then we'll talk about the uniqueness. So this statement is both about there is and there is unique. So it's an existence and a uniqueness claim. So first to discuss the existence. So fix a phi. Okay. So if phi were 0, then there was nothing to do. If phi is equal to 0, then phi is this guy clearly. So then we are done. So we may assume that phi is non-zero. Okay, so let H be the kernel of phi. And therefore the dimension of H is 1 less than the dimension of V. Immediately by rank nullity. So let's say this is H. And let us consider the orthogonal complement of H. Okay, so this is the orthogonal complement of H. Clearly, this is a one-dimensional subspace. Okay, so we may pick a unit vector. This has norm 1. Right, just pick anything non-zero in H perp and normalize it to get a unit vector. All right. And now let phi uv equal to lambda. Lambda is some scalar. And now we construct our vector, candidate vector, define v as lambda bar u. Okay. So if we were working with real inner product spaces, then lambda bar would be same as lambda. But because we may be working with a complex vector space, we have to use the conjugate. We will see why this comes about in a moment. So the claim is, which will prove the existence, phi is this guy. Okay. So the proof is very simple. Let W in the vector space be arbitrary. Want to show that this is the case, right? So write W as h plus mu u, where h is in kernel phi and mu is some scalar. So we can write it in this fashion because the vector space is the direct sum of h and h perp. So this comes from h, the little h comes from h, and this guy is the member in h perp. H perp is spanned by u, so it is going to be a scale of u. So we can write it this way. And therefore, what is phi w? By linearity of phi, this is equal to phi h plus mu phi u, which is 0 plus mu lambda. Okay, which is mu lambda. So I may just erase this 0. This is just mu lambda. But what is w dot v? So w dot v is h plus mu u dot v, which is equal to h dot v plus mu u dot v, where v is, as we defined, lambda bar u. And h dot v is 0 because, again, v is what? V is, okay, so let me substitute later. So this is v, and now v is lambda bar u. But this is 0. The first part is 0 because h and u are orthogonal, plus mu lambda u dot u, which is mu lambda. So indeed, this expression and that expression are equal because both of them are equal to mu lambda. So this proves the existence, and uniqueness is an exercise. It's an exercise because if you just take v1 and v2 such that these two things, the corresponding things, are equal, it will be forced that v1 is equal to v2. That's a very simple fact. Okay. So an immediate corollary is the following. If V is an inner product space, then this map, which takes a vector to the corresponding functional, is a bijection. So if the inner product space were linear, then, sorry, what am I saying? If the inner product space were real, then this would be a linear map. So that I want you to check. So check. If V is a real vector space, then this is a linear isomorphism. So bijection is clear from the previous fact, and linearity is just a very simple one-line check. So if V were real, then this is in fact a linear isomorphism. But if V were complex, then this is not quite a linear map. There is a conjugate problem here. If you, for instance, scale V by lambda, what you get is this, but this is not lambda times this thing, it is lambda bar times this thing. So there is a conjugate linearity going on, which is why this is not quite a linear map if the vector space V were complex. But nevertheless, it is a bijective function, and that is all we need. So now we can define the adjoint of a linear map. So fix two inner product spaces and a linear map between them. Okay, so we want to define the adjoint of T. Here is how we do it. So we have T going from V to W, and we just learned that we have these bijections. Sorry, so T is going from V to W, but we are not interested in T. We are interested in the transpose. So we have the map T transpose going from the dual of W to the dual of V, and we have these bijections. Okay, so the first bijection is nothing but W going to this guy, and the second is V going to this guy. All right. So now this is a bijection, this is a linear map, and since this is a bijection, we can go this way by inverting the map. So there is this path which goes from W to V, and that map is what we denote by T star. So this will be denoted by T star, and the notation is quite perverse. Here we were dualizing the vector spaces, and the corresponding dualization of the linear map is decorated by a T symbol, while here suddenly there is a star symbol. The good terminology or the good notation would be star should appear here, and here we should have some other notation, but textbooks do this, so I am doing this. So this is T star, and T star is called the adjoint of T. So we have defined the adjoint. It is unclear as to whether or not even if it is a linear map. You can immediately check that it is a linear map, but let me write a claim that will make it even more easier to check. So here is the claim. Okay, that's the claim, and let's prove it. Proof is just following this diagram. You just follow this diagram, you get the proof. So start with a vector W in the space W. You go up, you get this guy. Okay, you apply the transpose, you get this guy. And if you had applied the adjoint, meaning T star, you would get T star W. And to T star W, if you apply the vertical map, you would get this thing. But of course, these two things have to be equal, right? This is equal to that because once we went this way, the other time we went that way, but they have to lead to the same output. So we deduce that T transpose of this is equal to that. This is true for all W. And hence, right, we just fed V to both sides of that, and now it's just a matter of unpacking the definitions. And that's it. So that proves this claim. And using this claim, you can establish linearity of T star. Okay? So anyway, I leave that to you. So check that T star is linear. And in fact, there is a unique linear map in place of this guy which satisfies this equation. So this is a defining equation for the adjoint. We define adjoint in a different way. So here is the point. When we have two vector spaces V and W, you get a map from W star to V star, which is the transpose of the map. We are just trying to push that information to the original parent spaces. Rather than working with the dual spaces, we just want to work with the original spaces. And we are just pushing this information back to the original spaces via these identifications. So T star is the avatar of transpose that manifests itself because of the device of the inner product. If you have, let's say, just some non-degenerate bilinear form, that also allows you to identify W with its dual. And so non-degenerate bilinear forms also allow you to create similar objects. But we haven't discussed it, so let's keep it aside. When you have an inner product, you can definitely do it. Okay, so we have the notion of adjoint in our hands. Here are some properties of the adjoints. If V and W are inner product spaces and T is a map from V to W, a linear map I mean, then you have these following properties. So all are very, very easy to prove. Additivity means you add first and apply adjoint, or you adjoint first and add, it's the same thing, and so on and so on. You should read all of them. This is a nice one. So let me just prove the product rule, and then we'll be done. So to prove the product rule, we just need to check that. So first of all, what we have is, so when write product rule, we have to say something. So here S is a linear map from U to V, and T is from V to W. These are linear maps. This is another inner product space, and then this is the case. Then only this makes sense. So to check this, all you need to do is you dot so ST star is a map from W to U. Okay. So ST, sorry, what am I doing? I'm getting terribly confused. So S composed with T, this does not even make sense. This does not even make sense. So here T is a map from V to W as we have, but S is a map from W to something, and I do not want to write U, but anyway, so let's write U. It's a very horrible notation. Okay, so now S composed with T makes sense because the target of T is the domain of S. And now here is what we want to check. So ST of V, then you have little u, this is equal to TVS star U by the fact, just by the property of the adjoint of S, which is equal to VT star S star U. This is for all V in V and U in the space U. And therefore, I mean, we could have directly written that this is equal to that by definition of the adjoint of ST. And therefore, this expression and that expression are the same for each V and for each U, for each U, which just forces that this is equal to that. So that's it. I mean, this is how you can prove all of these things. Or you can go by the definition that we have here, the diagram, which I find much neater. Okay, if you make just two consecutive diagrams of this sort, one is going from W star to V star, one from U star to W star, you just successively write those diagrams, you get the correct thing. Okay. So yeah, fine. So all of these I leave as exercises. And lastly, we have this relationship between kernels and images, between the adjoint and the original map. So V and W be inner product spaces. T be some linear map from V to W. Then the kernel of the adjoint is the orthogonal complement of the image of T. And similarly, the second one, we will come to that. But first, let us prove this. So W is in kernel T star if and only if T star W is 0, which happens if and only if V dot T star W is 0 for all V, which happens if and only if TV dot W is 0 for all V, which happens if and only if TV is in the, or rather W is in the orthogonal complement of, W is orthogonal to TV for all V, which is same as saying that W belongs to the orthogonal complement of the image of T. Right? So W is in the kernel of the adjoint if and only if W is in the image of the orthogonal complement of the image of T. And therefore we have that equality. And for this part, first note that if W is in, or rather V is in image T star, then V equals T star W for some vector in W, which implies V dot which implies V is orthogonal to, or V belongs to the orthogonal complement of the kernel of T. So why is that implication there? Because if you have something in the kernel of T and you, let's say maybe X is in the kernel of T, then this is equal to W dx, which is equal to W0, which is equal to 0. Right? So if you have anything in the kernel of T, then this would be 0, and hence this guy is in the orthogonal complement of the kernel. So what this shows is whenever you pick something in the image of the adjoint, you get that the same thing lies in the kernel of the transpose. So we have this containment by the above reasoning. We have this containment, but these two things have the same dimension. Why? Because this is true. If you use this, you can immediately show that the dimension of this and the dimension of that are the same, and hence this must be an equality. And that's it. That proves both these things. So I will leave it at that, and I will see you next time.